What if a rogue black hole entered our solar system? Imagine standing beneath a night sky you've known your entire life, the constellations in their familiar places, the moon casting its gentle glow across the landscape. Now imagine that tomorrow, everything changes. Not gradually, not over millions of years, but suddenly, catastrophically. Without warning, an invisible predator tears through our solar system. A cosmic monster so powerful that it bends reality itself, warping space and time as it passes. This isn't science fiction. This is the terrifying possibility that keeps astrophysicists awake at night. What if a rogue black hole entered our solar system? Close your eyes for a moment and consider this question. How much do you really know about what's traveling through the darkness between stars? Right now, as you listen to these words, there could be something out there, hurtling through the void at speeds we can barely comprehend, heading directly toward us. We've mapped the planets, tracked asteroids, monitored comets, but there's something far more sinister that could be approaching, something we might not see until it's already upon us. A stellar corpse, compressed into a point so dense that not even light can escape its grip, wandering alone through the galaxy like a ghost ship sailing through an endless ocean. The universe is not the stable, predictable place we once imagined. Between the stars, in the vast emptiness of interstellar space, there are wanderers, rogues, objects that have broken free from their original homes and now drift aimlessly through the cosmic dark. Among these nomads, none is more terrifying than a rogue black hole. These objects represent the ultimate conclusion of stellar death. Points in space where gravity has become so intense that the very fabric of reality tears apart. Before we can understand what would happen if one entered our solar system, we need to understand what these objects truly are. A black hole isn't actually a hole at all. It's the opposite, in fact. It's matter compressed to such incredible density that it creates a gravitational well from which nothing can escape once it crosses a boundary called the event horizon. Think of space-time like a rubber sheet stretched tight. Place a marble on it, and it creates a small depression. Place a bowling ball, and the depression deepens. Now imagine placing something infinitely heavy on that sheet, so heavy that it doesn't just create a depression but punches straight through, creating a bottomless pit. That's essentially what a black hole does to the fabric of space-time. The concept sounds like something from a nightmare, and in many ways, it is. Black holes were first predicted by Einstein's equations of general relativity in 1915, but even Einstein himself was disturbed by the implications. For decades, scientists debated whether these objects could actually exist in nature or if they were merely mathematical curiosities, theoretical impossibilities that the universe would never actually produce. Then we found them. Not just one or two, but thousands. Millions, perhaps billions scattered throughout the cosmos. Most black holes we know about fall into two categories. There are stellar mass black holes, formed when massive stars exhaust their nuclear fuel and collapse catastrophically in supernova explosions. These typically range from 3 to dozens of times the mass of our Sun, compressed into a sphere just a few kilometers across. Then there are the supermassive black holes, monsters millions or billions of times more massive than our Sun, lurking at the centers of galaxies, including our own Milky Way. But what we're concerned with here is something different. A rogue, a wanderer, a stellar mass black hole that has somehow been ejected from its original location and now travels alone through the galaxy. How does a black hole go rogue? The mechanisms are terrifyingly simple. In dense stellar environments like globular clusters or the cores of galaxies, black holes can interact gravitationally with other massive objects. Imagine a cosmic game of billiards where the balls are stars and black holes, each interaction sending objects careening in new directions. When two black holes in a binary system merge, the asymmetric emission of gravitational waves can provide a powerful kick, launching the resulting black hole away at speeds that can reach thousands of kilometers per second. In other scenarios, close encounters with other massive objects in crowded stellar neighborhoods can slingshot a black hole out of its original system, sending it wandering through interstellar space like a bullet fired into the dark. The Milky Way galaxy is home to an estimated 100 million to 1 billion stellar mass black holes. Let that number sink in for a moment. 100 million to 1 billion invisible predators scattered throughout our galaxy, each one capable of destroying anything that comes too close. Most of these are likely in orbit around the galactic center, following predictable paths, but some portion, perhaps millions, are rogues. They've been kicked out of their original systems and now travel through the galaxy on their own trajectories. Impossible to see directly, detectable only by their gravitational effects on nearby matter or light. Have you ever considered how much of space is actually empty? The distances between stars are so vast that even if a rogue black hole were traveling at a significant fraction of the speed of light, the chances of it encountering any particular star system seem impossibly small. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. That's about 40 trillion kilometers. Space is big. Incomprehensibly, mind-numbingly big. This should be comforting. The sheer vastness of space should mean we're safe, that the probability of a rogue black hole specifically targeting our solar system is so infinitesimally small that we shouldn't worry about it. But probability isn't the same as impossibility. Scientists estimate that a star like our Sun might have a close encounter with another star once every few million years. The probability of a rogue black hole passing through our solar system is much lower, perhaps once every few billion years. But the universe is old, and it will be much older still. More importantly, low probability doesn't mean zero probability. Somewhere in the galaxy right now, there could be a rogue black hole on a trajectory that will bring it through our solar system. Not in a million years, not in 1,000, perhaps in our lifetimes, perhaps tomorrow. The truly disturbing part is that we might not know it's coming. Black holes don't emit light. They're the ultimate stealth predators. We can detect them only indirectly, through their gravitational effects. If a black hole passes near a star or accumulates matter from its surroundings, that matter heats up as it spirals inward, emitting X-rays and other radiation that we can detect. But a rogue black hole traveling through empty space? It would be completely dark, a moving wound in space-time, invisible until it was already upon us. Let me paint you a picture of what would happen. The scenario depends critically on several factors: the mass of the black hole, its speed, and most importantly, its trajectory. A black hole passing through the outer reaches of our solar system would be very different from one plowing through the inner planets. Let's explore both possibilities, and everything in between. Imagine first a best-case scenario, if such a thing can be said to exist. A stellar mass black hole, perhaps 5 times the mass of our Sun, enters the solar system from above the ecliptic plane, the flat disk where most planets orbit. It's traveling fast, maybe 100 kilometers per second, a typical velocity for stars in our galactic neighborhood. Its trajectory takes it through the outer solar system, beyond the orbit of Neptune, through the Kuiper belt where Pluto and countless icy bodies reside. Even at this great distance, the effects would be profound. The Kuiper belt objects, those frozen remnants from the solar system's formation, would feel the gravitational tug of the intruder. Some would be pulled from their stable orbits, sent careening toward the inner solar system or flung out into interstellar space. Imagine a cosmic pinball machine suddenly tilted, sending balls flying in every direction. The number of comets entering the inner solar system would increase dramatically. The night sky would fill with comets, their tails streaming behind them as they fall toward the sun. From Earth, we would witness something unprecedented. The comet rate would increase from a few per year to dozens, then hundreds. Astronomers would scramble to track them all, their telescopes trained on the sky night after night, watching the parade of icy visitors. But they would also notice something else, something deeply disturbing. The orbits of the outer planets would begin to change. Neptune, Uranus, Saturn, Jupiter, each would feel the gravitational influence of the passing black hole. Their orbital velocities would shift, their paths would curve, their positions in the sky would deviate from centuries of precise predictions. Can you imagine the confusion this would cause? For hundreds of years, we've used the orbits of planets as cosmic clockwork, so precise that we can predict their positions decades or centuries in advance. Suddenly, inexplicably, they would start to deviate. At first, it might seem like measurement error. Instruments malfunction. Data gets corrupted. But as multiple observatories confirmed the same anomalies, the truth would dawn on the astronomical community. Something massive, something invisible, was disturbing the solar system. The race would then begin to determine what was causing the disturbance. Teams of scientists would analyze the orbital perturbations, working backward from the effects to determine the cause. They would calculate the mass of the intruder, its speed, its trajectory. They would model its path through the solar system, determining where it had been and, more critically, where it was going. And then, depending on the trajectory, they would face the terrifying question: is it heading toward Earth? Let's pause here and consider what you would do if you learned that a black hole was approaching Earth. Not in the abstract, not as a thought experiment, but as a real, imminent threat. How would you spend your final days if you knew that everything you've ever known was about to be torn apart by an invisible cosmic predator? Now let's consider a worse scenario. The black hole's trajectory takes it closer to the inner solar system, passing between Jupiter and Mars. Jupiter, the king of planets, massive enough to contain more than 300 Earths, would be the first to feel the full force of the intruder. The gravitational dance between Jupiter and the black hole would be spectacular and terrible. If the black hole passed close enough, it could capture Jupiter, pulling the giant planet from its orbit around the Sun and dragging it away into interstellar space. Imagine watching through a telescope as Jupiter, a planet that's been a constant in the night sky for all of human history, slowly drifts away, its light dimming as it recedes into the cosmic dark. Or, in a different scenario, the encounter could increase Jupiter's orbital velocity, sending it spiraling inward toward the Sun or outward toward the edge of the solar system. But Jupiter's fate would be only the beginning of our problems. Jupiter acts as a gravitational shield for the inner solar system, its massive gravity deflecting or capturing asteroids and comets that might otherwise threaten Earth. Without Jupiter in its proper place, the dynamics of the entire solar system would change. The asteroid belt between Mars and Jupiter would be disrupted. Some asteroids would be flung inward, creating a deadly shooting gallery for Earth, Mars, Venus, and Mercury. The gravitational effects would propagate through the solar system like ripples in a pond. Mars would feel the disturbance next, its thin atmosphere perhaps stripped away entirely by the gravitational stress. The two small moons of Mars, Phobos and Deimos, would likely be torn from their orbits, either crashing into the planet or flying off into space. And then there's Earth. Even if the black hole didn't pass directly near our planet, the gravitational perturbations would affect us. Earth's orbit around the Sun is not a perfect circle but an ellipse, and that orbital shape determines our climate. A slight change in Earth's orbital eccentricity or the tilt of its axis could trigger dramatic climate changes. Ice ages could begin or end. Sea levels would rise or fall. Weather patterns would shift. The delicate balance that makes Earth habitable could be upset in ways we can barely predict. The Moon would also be at risk. Earth and the Moon are a binary system, bound together by gravity in a dance that's been ongoing for more than 4 billion years. A passing black hole could disrupt this relationship. The Moon could be pulled from Earth's orbit, leaving us moonless. Consider what that would mean. No more tides, or rather, much weaker tides driven only by the Sun. Earth's axial tilt would become unstable over geological time, causing wild climate swings. The night sky would be permanently changed, the Moon's familiar face gone forever. But these scenarios, as catastrophic as they sound, are still not the worst-case possibility. Let's consider the nightmare scenario, the one that represents an extinction-level event not just for humanity but potentially for all life on Earth. The black hole passes directly through the inner solar system, its path taking it near Earth itself. First, you would notice the stars behaving strangely. As a black hole approaches, it bends light passing near it, an effect called gravitational lensing. Stars in the direction of the approaching black hole would appear to shift position, creating a distorted region of the sky. This distortion would grow as the black hole approached, eventually creating a circular pattern where light from background stars is bent around the black hole's event horizon. At the very center would be a perfectly circular region of absolute blackness, a silhouette against the stars, growing larger night by night. Astronomers would calculate its trajectory with increasing precision, and the news would spread like wildfire. A black hole, heading directly toward us. Governments would convene emergency sessions. Scientists would be interviewed around the clock. The internet would explode with information, misinformation, panic, and denial. Some would pray. Some would riot. Some would simply go home to be with their families, to spend whatever time remained in the company of those they love. As the black hole approached, its gravitational effects would become apparent. The ocean tides, normally driven by the moon and sun, would begin to exhibit strange patterns. Water would be pulled toward the approaching black hole, creating unusual tidal bulges. Earthquakes would increase in frequency and severity as the Earth itself is stretched by tidal forces. These are the same forces that would eventually tear apart any object that crosses a black hole's event horizon, appropriately named spaghettification because objects are stretched like spaghetti noodles. The atmosphere would begin to behave erratically. Winds of unprecedented strength would circle the globe as air masses are pulled toward the intruder. The jet streams would destabilize. Weather patterns would become chaotic and unpredictable. Hurricanes and tornadoes would form in unusual locations and seasons. And then, if Earth were on a direct collision course with the black hole's event horizon, the end would come swiftly. The tidal forces would intensify beyond anything the planet could withstand. The crust would crack and buckle. Volcanoes would erupt worldwide. The oceans would boil away, the atmosphere would be stripped off, and the planet itself would be torn apart, broken into fragments that spiral inward toward the event horizon. As matter approaches a black hole, it doesn't simply fall straight in. Instead, it forms an accretion disk, a swirling maelstrom of material orbiting the black hole at tremendous speeds. Friction within this disk heats the material to millions of degrees, causing it to emit intense radiation. If Earth were being consumed by a black hole, the material from our planet would heat up as it spiraled inward, emitting X-rays and gamma rays. The irony is that as Earth died, it would briefly become one of the brightest objects in the solar system, a funeral pyre visible across light years of space. Once matter crosses the event horizon, it's gone from our universe in any meaningful sense. It has entered a region where space-time is so severely curved that all paths lead inward, toward the singularity at the black hole center. What happens at the singularity is one of the greatest mysteries in physics. Our current theories break down under such extreme conditions. General Relativity predicts infinite density, infinite curvature of space-time, a point where the laws of physics as we know them cease to function. Quantum mechanics suggests something else might happen, but we don't yet have a complete theory of quantum gravity to tell us what. Let's step back from this nightmare scenario and consider the science more carefully. How likely is any of this to actually happen? The probability is reassuringly low. The galaxy is vast, and rogue black holes, while numerous, are spread across enormous volumes of space. Researchers have calculated that the probability of a stellar mass black hole passing through the solar system close enough to cause significant disruption is extremely small, perhaps once every few trillion years. The universe itself is only about 13.8 billion years old, so the odds seem to be in our favor. However, there's an important caveat to these probability calculations. They assume we know how many rogue black holes are out there and how they're distributed. But the truth is, we don't really know. Black holes are difficult to detect unless they're actively accreting matter or gravitationally lensing background light. There could be many more rogue black holes wandering the galaxy than we currently estimate, and their distribution might not be uniform. Regions of the galaxy with higher stellar density might produce more rogues, and the dynamics of the Milky Way could concentrate them in certain areas. Some scientists have speculated about the existence of primordial black holes, hypothetical objects that could have formed in the first moments after the Big Bang rather than from stellar collapse. These could have a wide range of masses, from microscopic to thousands of solar masses. If they exist in significant numbers, they could make up some or all of the mysterious dark matter that we know exists but can't directly detect. A primordial black hole passing through the solar system would be indistinguishable in its effects from a stellar mass black hole of the same size. There's another proposal sometimes suggested, and it's even more elaborate. What if we detonated multiple nuclear weapons around the hurricane, creating blast waves that converge on the center and collapse the structure? Setting aside the logistical nightmare of coordinating multiple nuclear detonations in precise timing around a moving storm system, this idea fails for the same fundamental reasons. The energy mismatch is still enormous. The hurricane's power source is still intact. And now, instead of contaminating the environment with one nuclear weapon, you're using several, multiplying the radioactive fallout and the environmental damage. You'd create a scenario where multiple plumes of radioactive material are being mixed into the hurricane circulation from different points, ensuring even more widespread contamination. It's a solution that takes a bad idea and makes it exponentially worse. Let's talk about the political and international implications, because this isn't just a scientific or environmental issue. The use of nuclear weapons is governed by international treaties and norms that have been carefully constructed over decades to prevent nuclear conflict and limit proliferation. The Limited Test Ban Treaty of 1963 prohibits nuclear weapons tests in the atmosphere, in outer space, and underwater. It was signed specifically because atmospheric testing was spreading radioactive fallout globally, causing measurable increases in background radiation and raising cancer rates. Using a nuclear weapon to attack a hurricane would violate this treaty. It would constitute an atmospheric nuclear detonation, and it wouldn't matter that the intent was supposedly peaceful or defensive. The radiation doesn't care about intentions. The fallout would spread regardless. Moreover, imagine the international response. The United States detonates a nuclear weapon in the Atlantic Ocean or the Caribbean to try to stop a hurricane. That radioactive fallout doesn't respect borders. It spreads with the wind and the ocean currents. Caribbean nations, Central American countries, potentially parts of South America, and even Europe, depending on atmospheric circulation, could all receive fallout from this action. They weren't consulted. They didn't consent. But they're bearing the consequences of another nation's decision to use nuclear weapons in the shared global environment. This would be seen as an act of aggression, or at minimum, an act of criminal negligence. The political fallout, if you'll pardon the pun, would be immense. International condemnation, potential sanctions, the erosion of treaties and norms that have kept nuclear weapons largely in use since 1945, all of this could result from an attempt to nuke a hurricane. There's also the domestic political dimension. Public opinion on using nuclear weapons for any purpose is complex and often divided. Even framing it as a defensive measure against natural disasters wouldn't necessarily create consensus. Many people would rightly be horrified at the idea of intentionally releasing radiation into the environment. Environmental groups would oppose it. Public health organizations would oppose it. Neighboring countries would oppose it. The political cost of even proposing such an action seriously, let alone implementing it, would be staggering. And if it didn't work, if the hurricane kept coming and now it was radioactive, the political leaders who authorized the action would face consequences that would make typical political scandals look trivial by comparison. You'd be responsible for both failing to stop the hurricane and for deliberately contaminating vast areas with radiation. It's a lose-lose scenario of almost unprecedented magnitude. Now let's examine some of the scientific studies that have actually been conducted on this question, because despite all the obvious problems, researchers have actually modeled what would happen if we nuked a hurricane. These studies aren't advocacy. They're not recommendations. They're scientific analyses done to definitively answer the question and, hopefully, put it to rest. One of the key findings from these studies involves the temperature change that a nuclear explosion would create in the hurricane. A nuclear weapon releases tremendous heat, yes, but that heat dissipates quickly, and the volume of air and water involved in a hurricane is so vast that the temperature change would be negligible. One study calculated that even a very large nuclear explosion would raise the temperature in the hurricane by less than 1 degree Celsius, and that's being generous with the assumptions. 1 degree in a storm system that's already dealing with temperature differentials and energy flows thousands of times larger. It would be completely insignificant. The hurricane wouldn't notice. Another finding relates to the blast wave and wind disruption. The blast wave from a nuclear explosion travels outward at supersonic speeds initially, but it weakens rapidly with distance. In the open atmosphere, especially in the chaotic environment of a hurricane where winds are already extreme, the blast wave dissipates quickly. Within a few miles of the detonation, the effect would become indistinguishable from the hurricane's own wind fluctuations. You're not creating enough sustained force to counteract the hurricane's circulation. You're creating a brief pulse that gets absorbed into the larger system. It's like clapping your hands once to try to stop a freight train. The energy you're inputting is real, but it's trivial compared to the momentum of what you're trying to stop. Some researchers have also explored whether you could use nuclear explosions to somehow heat the upper atmosphere above a hurricane, creating conditions that might disrupt its vertical structure. Hurricanes need a particular vertical temperature profile to maintain themselves. If you could dramatically alter that profile, in theory, you might weaken the storm. But the calculations show that heating the upper atmosphere over a hurricane would require sustained energy input at levels we simply cannot achieve. A single explosion wouldn't do it. Even multiple explosions wouldn't do it. You'd need continuous energy input over a large area for an extended period, and we don't have any technology that can do that, nuclear or otherwise. And again, even if we could, the radioactive contamination would make the cure far worse than the disease. Have you considered whether we're actively looking for rogue black holes? The answer is yes, though not always directly. Several astronomical surveys monitor the sky for various phenomena, and some of these could potentially detect a rogue black hole. One method is looking for gravitational microlensing events. When a massive object passes between us and a background star, the object's gravity bends the star's light, causing the star to temporarily brighten in a characteristic way. By monitoring millions of stars, we can detect these lensing events and, from the light curve shape and duration, calculate the mass of the lensing object. Several surveys have detected microlensing events consistent with stellar mass compact objects, possibly black holes, wandering through the galaxy. In 2022, researchers announced the detection of what may be a rogue black hole about 7 solar masses, located about 5,000 light-years from Earth. It was detected through its gravitational lensing effect on a background star. The event lasted several hundred days, much longer than typical microlensing events caused by stars, suggesting that the lensing object was very compact and massive, consistent with a black hole. This detection is significant because it confirms what theory has long predicted: rogue black holes are out there. They're not just mathematical possibilities but physical realities, wandering through our galaxy. The discovery raises an interesting question. How many more are out there that we haven't detected? Current microlensing surveys can detect only those rogues that happen to pass between us and stars we're monitoring. The vast majority of rogue black holes wouldn't be detected by this method because they don't happen to cross our line of sight to any particular star. Other detection methods are being developed. The Vera Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, photographing the entire visible sky every few nights. This unprecedented survey will detect numerous transient and moving objects, and it might catch the signatures of rogue black holes through gravitational lensing or interactions with interstellar matter. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct extensive microlensing surveys that should detect many more lensing events, potentially revealing the population of compact objects, including black holes, wandering through the Milky Way. Even with these advanced instruments, however, detecting a rogue black hole heading specifically toward the solar system would be challenging. Unless it happened to lens a background star, or unless we got incredibly lucky with our surveys, we might not detect an incoming rogue until it was relatively close, perhaps already within the outer solar system. By that point, would we have enough time to do anything about it? This brings us to an uncomfortable question. If we detected a rogue black hole heading toward the solar system, could we do anything to protect ourselves? The honest answer is almost certainly no. Black holes are governed by gravity alone, and we have no way to shield against gravity or significantly alter the trajectory of such a massive object. Our most powerful rockets struggle to send small payloads to the outer planets. The idea of moving something with the mass of multiple suns is beyond absurd. Some science fiction scenarios imagine using powerful explosions to alter the course of dangerous objects, but this strategy works only for small bodies like asteroids, and even then, it requires significant lead time and precise planning. You can't deflect a black hole with a nuclear explosion or any other kind of force we can currently generate. The energy scales involved are simply too vast. A stellar mass black hole has more momentum than entire star systems. Nothing we could do would meaningfully change its course. So if we couldn't stop it or deflect it, what could we do? The only option would be evacuation, but even that presents nearly insurmountable challenges. Where would we evacuate to? If a black hole is disrupting the entire solar system, nowhere in the solar system is truly safe. We would need to leave entirely, traveling to another star system. But we don't have that capability. Our current spacecraft travel at tiny fractions of the speed of light. Even our fastest probes would take tens of thousands of years to reach the nearest stars. There are theoretical propulsion systems that could achieve much higher speeds. Fusion rockets, antimatter drives, laser-pushed light sails. But these are decades or centuries away from practical implementation, if they're possible at all. Even if we had the technology, building evacuation ships for 8 billion people, or even a small fraction of humanity, would require resources and time we wouldn't have if a black hole were already approaching. The cold reality is that if a rogue black hole entered our solar system on a collision course with Earth, we would be helpless to stop it. Humanity would face its end not with a bang but with a whimper, watching the sky distort and darken as the invisible predator closed in. This helplessness in the face of cosmic forces is humbling. We like to think of ourselves as masters of our environment, capable of overcoming any challenge through technology and ingenuity. But the universe is full of forces so powerful that our greatest achievements are insignificant by comparison. Yet there's something profound to be learned from contemplating such scenarios. They remind us of our place in the cosmos. We live on a fragile world, a tiny oasis of life in a vast and often hostile universe. Our existence here is not guaranteed. It's a contingent fact, dependent on countless variables being just right. The Earth orbits at the right distance from the Sun for liquid water to exist. Our moon stabilizes our axial tilt, creating a stable climate. Jupiter shields us from many comet impacts. We haven't been hit by a civilization-ending asteroid in 65 million years. A rogue black hole hasn't torn through our solar system. How much of this is luck? How much is the anthropic principle at work? The idea that we observe these favorable conditions precisely because they're necessary for our existence. If conditions were different, we wouldn't be here to observe them. Somewhere in the galaxy right now, there might be star systems being disrupted by rogue black holes, planets being torn apart, ecosystems being annihilated. But there's no one there to witness it, or if there was, they're gone now. This leads to some fascinating philosophical questions. If a rogue black hole destroyed Earth and all evidence of human civilization, would our existence have mattered? We've been sending radio signals into space for about a century, so there's a bubble of radio waves expanding outward from Earth at the speed of light, currently about 100 light-years in radius. These signals are incredibly faint and probably wouldn't be detected by anyone unless they were specifically listening. But they're out there, a whisper of proof that we existed. We've also sent a few physical artifacts beyond the solar system. The Pioneer and Voyager spacecraft, carrying plaques and golden records with information about humanity. If Earth were destroyed, these artifacts would continue drifting through interstellar space, perhaps for billions of years, until they eventually fall into a star or are captured by some planetary system. Would these faint echoes be enough? Would it matter that we had existed, that we had wondered and explored, created art and music, loved and suffered, if all of it ended in an instant? These are questions without answers, but they're worth contemplating as we consider our cosmic vulnerability. Let's explore some more nuanced scenarios, because the outcome of a rogue black hole encounter depends heavily on specific circumstances. Not all encounters would be catastrophic. Some could even be, in a strange way, scientifically valuable. Imagine a small black hole, perhaps just 3 to 5 solar masses, passing through the outer solar system, beyond Neptune's orbit. At this distance, the gravitational effects on the inner planets would be minimal. We might see some perturbations in the orbits of Kuiper belt objects and an increased comet rate, but Earth itself would be largely unaffected. This scenario would present an unprecedented scientific opportunity. For the first time, we would have a black hole close enough to study in detail. Every telescope on Earth and in space would turn toward it, observing its gravitational lensing effects, its interaction with the solar wind and the interstellar medium. We could measure its mass with unprecedented precision, study the space-time curvature around it, test general relativity in the strong field regime. It would be the discovery of the century, revolutionizing our understanding of these exotic objects. Scientists would track its trajectory with extreme precision, calculating whether it might return in the future or if this was a one-time passage. They would look for any signs of an accretion disk or jets, though a rogue black hole in the relatively empty space of the solar system probably wouldn't have much material to accrete. They would search for any companion objects, because if this black hole had been part of a binary system, its companion might have been ejected along with it. The public reaction would be fascinating. Some would panic, despite reassurances that the black hole posed no immediate threat. Others would be captivated, following the news coverage and looking up at the night sky, trying to spot the region of distorted stars. It would spark renewed interest in astronomy and physics, inspiring a new generation of scientists to study the cosmos. But even in this relatively benign scenario, there would be long-term consequences. The black hole's passage would alter the orbits of objects throughout the solar system. These changes would be small, but they would accumulate over time. Thousands or millions of years later, the solar system would be slightly different because of this encounter. Some asteroids might be placed on collision courses with planets. Some Kuiper belt objects might be sent sunward, creating unusual comet showers millennia hence. The effects would ripple forward through time, a permanent mark left by the wanderer's passage. Another scenario worth considering is a very close but non-collisional encounter. The black hole passes within the orbit of Mercury but doesn't directly hit any planet. The gravitational effects would be severe. Mercury might be torn from its orbit entirely, either crashing into the Sun or being ejected from the solar system. Venus and Earth would experience tremendous tidal stresses. The orbits of all the inner planets would be significantly altered. Earth's climate would change dramatically as its distance from the Sun and orbital eccentricity shifted. If we were moved slightly closer to the Sun, global temperatures would rise. Polar ice caps would melt, sea levels would rise by dozens of meters, and vast coastal regions would be flooded. If we were moved farther away, an ice age would begin. Glaciers would advance from the poles, covering much of North America, Europe, and Asia in ice kilometers thick. The change in orbital parameters would also affect the length of the year. If Earth's orbit became larger, the year would lengthen. Calendars would need to be recalculated. Seasons would shift in duration and intensity. The delicate astronomical calculations we use for navigation and timekeeping would all need to be redone. Humanity would face an unprecedented crisis, but unlike a direct collision, we might actually survive this scenario. The changes would be catastrophic, requiring massive adaptations in how and where we live, but at least Earth itself would remain intact, and some regions would remain habitable. This would test our resilience as a species. Could we adapt quickly enough? Could we manage the resource conflicts and mass migrations that would inevitably result? It's impossible to say, but it would certainly be the greatest challenge humanity has ever faced. Now, let's consider what scientists have actually found when looking for evidence of black holes, rogue or otherwise. The first black hole candidates were discovered in the 1970s through their X-ray emissions as they accreted matter from companion stars. Cygnus X1, discovered in 1964 and confirmed as a black hole in the 1970s, was the first. Since then, we've detected dozens of stellar mass black holes in binary systems within our galaxy. The direct detection of gravitational waves by LIGO in 2015 opened a new window into the universe. These ripples in spacetime, predicted by Einstein but undetected for a century, are produced when massive objects like black holes spiral together and merge. The first detection, designated GW 1500914, came from the merger of two black holes about 30 solar masses each, located over 1 billion light-years away. Since then, LIGO and other gravitational wave observatories have detected dozens more black hole mergers. These detections are remarkable for several reasons. First, they confirm that black holes exist and behave exactly as general relativity predicts. Second, they reveal a population of black holes more massive than we expected from stellar evolution models, suggesting we don't fully understand how the most massive stars die. Third, and most relevant to our topic, these mergers can produce recoil kicks that turn the resulting black hole into a rogue, ejecting it from its host galaxy at high speed. Some of the black hole mergers detected by LIGO show evidence of these kicks. The gravitational waves carry information about the masses and spins of the merging black holes, and from this, physicists can calculate the recoil velocity of the final black hole. Some of these kicks are powerful enough to exceed the escape velocity of massive galaxies, meaning the merged black hole would be ejected entirely, becoming an intergalactic wanderer. These rogues would travel through the vast voids between galaxies, perhaps for billions of years, until chance brings them into another galaxy or they encounter something interesting. Within our galaxy, stellar dynamics can also create rogues. The Milky Way has numerous globular clusters, dense spherical collections of hundreds of thousands of stars orbiting the galactic center. These clusters are crowded environments where stars and stellar remnants frequently interact gravitationally. Computer simulations of globular cluster evolution show that black holes can sink to the cluster center through a process called mass segregation, where more massive objects settle toward the middle while less massive stars are pushed outward. In the cluster core, black holes can form binary systems with each other or with neutron stars. These binaries interact with passing stars, and these interactions transfer energy. Sometimes the interactions are strong enough to eject one or more of the objects entirely from the cluster. Researchers estimate that globular clusters could have ejected many stellar mass black holes over their lifetimes, sending rogues wandering through the galaxy. The galactic center is another likely source of rogue black holes. At the very heart of the Milky Way sits Sagittarius A star, a supermassive black hole about 4 million times the mass of the Sun. The region around Sagittarius A star is crowded with stars, many in highly elliptical orbits that bring them very close to the central black hole. Some stars get too close and are torn apart by tidal forces in events called, appropriately, tidal disruption events. But stellar mass black holes are more resilient. They can survive close approaches to the supermassive black hole and, in the process, receive gravitational kicks that send them flying out of the galactic center at high velocities. These mechanisms, merger recoils, cluster ejections, and galactic center kicks, populate the galaxy with rogue black holes. Most follow orbits around the galactic center, just like stars do, but their trajectories are randomized, no longer tied to any specific system or structure. They're cosmic wanderers, and their paths could take them anywhere, including through our solar system. Think about the cosmic history that each rogue black hole represents. Each one was once part of a massive star, perhaps dozens of times the mass of our Sun. That star spent millions of years fusing hydrogen into helium, helium into carbon, carbon into heavier elements, working its way up the periodic table. Then, when its fuel was exhausted, it collapsed catastrophically, releasing more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifetime. The outer layers were blown off in a supernova explosion, scattering heavy elements into space, the raw materials for future planets and life. But the core collapsed beyond the point of no return, compressing past the neutron degeneracy pressure that supports neutron stars, collapsing into a black hole. For some time after formation, the black hole might have remained in place, perhaps with a companion star, perhaps alone, orbiting the galactic center along with the other remnants of its stellar nursery. Then something happened. An encounter, a merger, a gravitational interaction that changed everything. The black hole was accelerated to high velocity, tearing free from wherever it had been. Now it wanders alone, a testament to the violent processes that shape our galaxy, invisible, silent, deadly. How many rogues are close to us right now? The nearest known black hole candidate is about 1,500 light-years away, part of a system with a visible star. But that's just the nearest one we've detected. There could be others much closer that we haven't found because they're not interacting with anything visible. Statistical models suggest there might be several stellar mass black holes within 100 light-years of the Sun. At these distances, they pose no threat, but it's a reminder that these objects are not as rare as we might hope. Imagine being able to see black holes with your naked eyes. If your vision could somehow detect gravitational fields instead of light, the night sky would look very different. Scattered among the stars, you would see dark spots, regions where space-time is warped, where reality bends inward. Some would be stationary, or nearly so, moving only with the general rotation of the galaxy. Others would be moving faster, their positions changing noticeably over months or years. These would be the rogues, the wanderers, passing through the stellar neighborhood on their lonely journeys. But we can't see gravitational fields directly, so the rogues remain hidden unless they betray their presence through interactions. This invisibility is one of the most unsettling aspects of the rogue black hole scenario. We have excellent surveys that track asteroids and comets, giving us warning of potential impacts years or decades in advance. But a rogue black hole might give us no warning at all until it was practically upon us. There's a related concern that some scientists have raised: intermediate mass black holes. These hypothetical objects would have masses between stellar mass black holes and supermassive ones, ranging from hundreds to hundreds of thousands of solar masses. The evidence for their existence is tentative. Some globular clusters show kinematic evidence of central massive objects that could be intermediate mass black holes. Some ultraluminous X-ray sources in other galaxies might be powered by intermediate mass black holes accreting matter. If intermediate mass black holes exist and some are rogues, they would be even more dangerous than stellar mass rogues. Their larger mass means stronger gravitational effects at greater distances. An intermediate mass black hole passing through the outer solar system could cause disruptions comparable to a stellar mass black hole passing through the inner solar system, and they would be just as difficult to detect. Then there's the truly exotic possibility: primordial black holes. These theoretical objects could have formed in the very early universe, within the first second after the Big Bang, from density fluctuations in the hot, dense primordial plasma. Primordial black holes could have any mass below about 100,000 solar masses, the maximum that could have formed this way. Most interestingly, they could be very small, even microscopic. A primordial black hole with the mass of a mountain would be smaller than an atom, yet it would still be a black hole, with an event horizon and all the associated properties. These tiny black holes could be far more numerous than stellar mass ones. Some theories suggest they could account for all or most of dark matter. If that's true, then these microscopic black holes are everywhere, passing through Earth and our own bodies constantly, completely unnoticed. A microscopic primordial black hole passing through your body right now wouldn't hurt you. Its event horizon is so tiny, and it's moving so fast, that it would zip through before you could notice anything. It would barely interact with ordinary matter at all. But a larger primordial black hole, one with the mass of the Moon or Earth, would be a different story. It would have all the gravitational effects of that mass, concentrated into an incredibly tiny volume. Such an object passing through the solar system would be just as dangerous as a stellar mass black hole, perhaps more so because we have even less evidence for their existence and abundance. Contemplating all these possibilities, you might feel a sense of cosmic anxiety. The universe contains many ways to destroy us, and we can protect ourselves from very few of them. Gamma ray bursts, supernovae, rogue stars, interstellar comets, and now rogue black holes. The list of cosmic threats is long and sobering. But here's some perspective. Earth has existed for 4.5 billion years, and life has persisted for most of that time. In all those eons, none of these catastrophes have completely sterilized the planet. Yes, there have been mass extinctions. The asteroid that killed the dinosaurs 65 million years ago wiped out 3/4 of all species. But life persisted, recovered, and diversified. Even the worst mass extinction in Earth's history, the Permian-Triassic event 250 million years ago, which killed up to 96% of all marine species, didn't end life entirely. Life is resilient. It adapts. It survives. A rogue black hole passing through the solar system would be different. Depending on its trajectory, it might be completely unsurvivable. But the probability is low, reassuringly low. In all likelihood, humanity will face many challenges in its future, but a rogue black hole won't be one of them. Still, the possibility exists, and contemplating it serves a purpose. It reminds us of our cosmic context, our fragility, our dependence on a universe that doesn't care about our survival. What would future civilizations, if they survive long enough, be able to do about rogue black holes? With sufficiently advanced technology, detection would become much easier. A network of gravitational wave detectors distributed throughout the solar system could sense the space-time ripples produced by massive objects moving nearby. Advanced telescopes could monitor the positions of millions of stars with such precision that even subtle gravitational lensing effects would be detected immediately. A rogue black hole approaching the solar system would be spotted decades or centuries before arrival. But detection is only the first step. Could an advanced civilization deflect or avoid a rogue black hole? The masses involved make deflection seem impossible, but perhaps there are strategies we haven't imagined. If you can't move the black hole, maybe you could move your planet. This sounds like science fiction, and it is, but it's not entirely absurd. A sufficiently advanced civilization might be able to use controlled gravitational interactions or powerful propulsion systems to gradually shift a planet's orbit. The timescales required would be enormous. Moving Earth to a different orbit would take centuries or millennia, even with technology far beyond our current capabilities. But if you had decades or centuries of warning about an approaching black hole, it might be possible. Alternatively, a civilization might choose to abandon its home planet entirely, building massive space habitats or generation ships to carry its population elsewhere. These speculations are fun to explore, but they're far beyond our current capabilities. For now, we're stuck with monitoring, hoping, and trusting in the vastness of space to keep the rogues away from us. It's a passive strategy, the only one available to us, and it has worked so far. The solar system has existed for 4.5 billion years without being destroyed by a rogue black hole. That's a pretty good track record. Let's return to the science of black holes themselves, because understanding these objects better helps us appreciate both their danger and their wonder. Black holes are predictions of general relativity, Einstein's theory of gravity. In general relativity, gravity is not a force in the traditional sense but a curvature of spacetime caused by mass and energy. Massive objects like stars and planets create depressions in the spacetime fabric, and other objects follow curved paths through this warped geometry, which we perceive as gravitational attraction. A black hole is what happens when this curvature becomes extreme. When a massive star collapses, it compresses a tremendous amount of mass into a very small volume. As the object becomes denser, the space-time curvature around it becomes more severe. Eventually, the curvature becomes so steep that it creates a region from which not even light can escape. The boundary of this region is the event horizon. The name is fitting. Once you cross the event horizon, no events happening to you can ever be observed by anyone outside. You're cut off from the external universe, causally disconnected. From your perspective, assuming you somehow survived the journey, you would cross the event horizon and continue falling inward. You might not even notice the exact moment you crossed it, because the event horizon isn't a physical barrier or surface. It's simply a point of no return, the place where the escape velocity exceeds the speed of light. After crossing the event horizon, you would continue falling toward the singularity. The tidal forces would grow stronger with every meter you descended. These forces arise because gravity is stronger closer to the massive object, so your feet, being closer to the singularity than your head, would be pulled harder. The difference in gravitational pull would stretch you vertically and compress you horizontally, hence the term spaghettification. For a stellar mass black hole, the tidal forces at the event horizon would already be lethal, tearing apart any normal matter. For a supermassive black hole, the event horizon is much farther from the singularity, so the tidal forces there are weaker. You might actually survive crossing the event horizon of a supermassive black hole, living for perhaps minutes or even hours as you fall inward before eventually being torn apart closer to the singularity. What happens at the singularity? That's where our physics breaks down. General Relativity predicts that all the mass of the black hole is compressed into a point of infinite density, a place where the curvature of space-time becomes infinite. But infinities in physics usually indicate that our theories are incomplete. Most physicists believe that a complete theory of quantum gravity would resolve the singularity, showing that something other than infinite density occurs there. But we don't yet have such a theory. Some speculate that the singularity might be a gateway to another universe, or another region of our own universe, a wormhole connecting distant points in space. There's no evidence for this, and most physicists are skeptical, but it remains a tantalizing possibility explored in theoretical physics and science fiction. Black holes also have some strange properties regarding time. From the perspective of a distant observer, an object falling toward a black hole appears to slow down as it approaches the event horizon, its clock ticking slower and slower due to time dilation. In principle, the object would appear to freeze at the event horizon, never quite crossing it, its light becoming infinitely redshifted and fading away. But from the perspective of the falling object, time continues normally, and it crosses the event horizon in a finite amount of proper time. This difference in perspectives is one of the most mind-bending aspects of general relativity. Both observers are correct within their own reference frames. Time really does flow differently in strong gravitational fields. If a rogue black hole passed very close to Earth, we would experience measurable time dilation effects. Clocks on the side of Earth closest to the black hole would run slightly slower than clocks on the far side. GPS satellites, which rely on precise timekeeping, would give incorrect positions as their clocks drifted out of sync. There's also the question of what happens to information that falls into a black hole. This might seem like an abstract concern, but it's actually one of the biggest unsolved problems in theoretical physics. Quantum mechanics says that information cannot be destroyed. The complete quantum state of a system can evolve and change, but the information is always preserved in principle. But black holes seem to destroy information. Anything that falls past the event horizon is gone, and the black hole is characterized by only a few parameters: mass, charge, and angular momentum. All the other details about what fell in are lost. Stephen Hawking discovered that black holes aren't completely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation causes black holes to slowly lose mass and eventually evaporate completely. But Hawking radiation, as originally calculated, is completely thermal, containing no information about what fell into the black hole. This led to the black hole information paradox. When a black hole evaporates, where does the information go? Decades of debate and research have led to some possible resolutions, involving holographic principles and quantum corrections to Hawking's calculation. But the paradox isn't completely resolved. If a rogue black hole consumed Earth, the information about every atom, every person, every book, every work of art would seemingly be lost forever, or perhaps encoded in subtle correlations in the Hawking radiation emitted over the black hole's remaining lifetime. These are deep questions, and contemplating them gives us a different perspective on the rogue black hole scenario. Yes, it would be a physical catastrophe, the destruction of our world. But it would also be a cosmic mystery, a place where our understanding of reality breaks down, where the rules we've discovered don't quite apply. There's something darkly beautiful about that, even as we hope it never happens to us. Now, let's think about historical close calls. Has Earth ever had a near miss with a rogue black hole? The answer is almost certainly no. If a stellar mass black hole had passed through the solar system in the last few billion years, we would probably see evidence of it. The orbital dynamics of the solar system are well understood and show no signs of recent major perturbations. The asteroid belt, the Kuiper belt, the Oort cloud all have structures consistent with billions of years of slow, steady evolution without major disruptions. However, there have been other types of close calls. About 70,000 years ago, a binary star system consisting of a red dwarf and a brown dwarf passed through the outer Oort cloud, coming within about 1 light-year of the Sun. This is the closest confirmed stellar encounter in the last few million years. The system, now called Scholz's star, would have been visible in the night sky to our human ancestors, though as a faint reddish point of light. The gravitational perturbations from this encounter might have sent some comets from the Oort cloud toward the inner solar system, though any effects would have been minor. Looking forward, we can predict future stellar encounters. The star Gliese 710 will pass within about 60,000 astronomical units of the Sun in about 1.3 million years. The star HIP 85605 will come even closer, perhaps within 25,000 astronomical units, though the timing is very uncertain. These encounters will perturb the Oort cloud and might increase the comet rate, but they won't threaten Earth directly. But these are encounters with ordinary stars, not black holes. A rogue black hole encounter would be far less predictable. We can track stars because we can see them, plotting their positions and velocities and calculating their future paths. Rogue black holes are invisible unless they happen to lens background light or interact with visible matter, so we can't predict their paths the same way. This brings us to an unsettling realization. Right now, there could be a rogue black hole heading toward the solar system, and we would have no way of knowing until it was close enough for its gravitational effects to become apparent. Depending on its speed and trajectory, we might have years, months, or even just weeks of warning. What would we do with that warning? The psychological impact would be profound. Humanity has faced existential threats before: nuclear war, climate change, asteroid impacts, pandemics. But all of these, in principle, are things we can do something about. We can negotiate arms reductions, cut carbon emissions, deflect asteroids, develop vaccines. A rogue black hole would be different. There would be nothing we could do. No negotiation, no mitigation, no defense. Just waiting for the inevitable. How would society react? Some would turn to religion, seeking comfort in faith and the promise of an afterlife. Some would pursue pleasure and distraction, living their final days to the fullest. Some would panic, leading to breakdowns in social order. Some would work feverishly on last-ditch scientific proposals, even knowing they were futile. And some would simply spend time with loved ones, finding meaning in connection even as the end approached. There would also be profound philosophical discussions. Does life have meaning if it can be ended so suddenly by impersonal cosmic forces? Or does the fragility of existence make our time more precious, our connections more meaningful? Different philosophical traditions would offer different answers. Existentialists might emphasize the importance of creating meaning in an indifferent universe. Religious believers might see it as part of a divine plan. Nihilists might shrug and say they always knew nothing mattered. But these discussions would be cut short by the reality of the approaching black hole. As it entered the solar system, the effects would become undeniable. Observatories would track the gravitational perturbations with increasing precision. News organizations would provide constant updates. The distortion in the star field would become visible to amateur astronomers, then to anyone looking up at the night sky. In the final days or hours, depending on the scenario, people would gather with their families and communities. Some would watch the sky, witnessing the cosmic drama unfolding. Some would pray or meditate. Some would simply hold each other, finding comfort in touch and presence. And then, depending on the specific trajectory, the end would come. Perhaps quickly, with Earth torn apart in minutes as it crossed the event horizon. Perhaps more slowly, with the planet's orbit disrupted, leading to climate catastrophes that play out over months or years. Either way, it would mark the end of the human story on Earth. A story that has lasted for hundreds of thousands of years. A story of struggle and triumph, of art and science, of love and loss. All of it would end not because of anything we did or failed to do, but simply because we happened to be in the wrong place at the wrong time, cosmically speaking. Yet even in this dark scenario, there's a strange kind of grandeur. We would be participants in one of the most dramatic events possible in the universe, the encounter between a planet full of life and one of the most exotic objects in nature. Our final act would be to witness and understand, to observe the universe even as it destroyed us. There's something noble in that, something quintessentially human. Of course, we all hope this scenario remains purely hypothetical. The probability is on our side. The universe is vast, and while it contains many dangers, it also contains vastness enough to keep most of them far away from us. For 4.5 billion years, Earth has orbited the Sun in relative peace, and there's every reason to think it will continue to do so for billions more, until the Sun eventually swells into a red giant and renders the planet uninhabitable in the natural course of stellar evolution. But the possibility of a rogue black hole, however remote, serves as a reminder. We live in a dynamic, sometimes violent universe. Our existence is contingent, dependent on countless factors beyond our control. This should inspire both humility and wonder. Humility because we're not the center of the universe, not protected by anything except distance and probability. Wonder because despite our cosmic insignificance, we're here, conscious and curious, able to understand the forces that could destroy us. This understanding is itself remarkable. For most of human history, black holes were beyond imagining. The idea that matter could collapse so completely that it tears a hole in space-time would have seemed like magic or madness. Yet through observation, mathematics, and reason, we've come to understand these objects. We've detected them, studied them, begun to unravel their mysteries. We've even photographed the shadow of a supermassive black hole, the one at the center of the galaxy M87, a feat that required coordinating telescopes across the entire Earth. Our growing understanding of black holes is part of a larger story of humanity reaching beyond our immediate environment to comprehend the cosmos. We've sent spacecraft to every planet in the solar system. We've landed robots on Mars and Titan. We've detected planets around other stars, thousands of them, some possibly harboring life. We've observed galaxies billions of light years away, looking back in time to when the universe was young. We've detected gravitational waves, ripples in space-time itself, confirming predictions made a century ago. All of this knowledge, all of this capability, has been developed in just the last few centuries, an eye blink in cosmic time. Imagine what we might achieve in the next few centuries if we survive and continue to advance. Perhaps we'll develop the technology to detect rogue black holes decades or centuries before they could threaten us. Perhaps we'll even develop the capability to protect ourselves through strategies we can't yet imagine. Or perhaps we'll spread beyond Earth, establishing colonies on other worlds, ensuring that humanity's eggs aren't all in one planetary basket. The rogue black hole scenario, terrifying as it is, can inspire us to think long-term about the survival and flourishing of our species. If we care about the future of humanity, we need to become a multi-planet species eventually. Not tomorrow, not next year, but on a time scale of decades or centuries. We need to develop the technologies and social systems that will allow us to thrive in space, to establish self-sustaining communities beyond Earth. This isn't just about avoiding rogue black holes or any other specific threat. It's about resilience, about not having all of our civilization concentrated on one fragile world. It's about continuing the story of human exploration and expansion, the same impulse that led our ancestors to cross oceans and continents, now extended to the cosmos. But we also need to appreciate and protect Earth. Despite its fragility in cosmic terms, it's the only home we have right now, and likely will be for generations to come. The same scientific understanding that reveals cosmic threats also reveals terrestrial ones, challenges that we ourselves are creating. Climate change, biodiversity loss, pollution, resource depletion. Unlike a rogue black hole, these are problems we can actually address if we choose to. There's an interesting parallel here. The vastness of space protects us from most cosmic threats through sheer distance and emptiness. But this protection isn't absolute, and it doesn't excuse us from preparing for dangers or addressing the problems we can control. Similarly, Earth's natural systems have buffered humanity against our own destructive tendencies for a long time. But this buffering has limits. We're testing those limits now. The lesson from contemplating cosmic catastrophes like rogue black holes is that we should cherish the time we have, protect the world that sustains us, and work toward a future where humanity can survive and thrive despite the challenges we'll inevitably face. Whether those challenges are cosmic or terrestrial, external or self-inflicted, our best hope is knowledge, preparation, and the wisdom to use both well. As we close this exploration of rogue black holes, let's return to the night sky. Tonight, when darkness falls, go outside if you can. Look up at the stars, those distant suns scattered across the galactic disk. Between them, invisible to your eyes, are the wanderers. Rogue planets ejected from their solar systems. Rogue stars cast out from star clusters. And yes, rogue black holes, silent and dark, following their solitary paths through the void. Most of these rogues will wander forever without encountering anything significant. The galaxy is vast enough to swallow them, to keep them isolated in the darkness between the lights. But occasionally, perhaps once in billions of years, a wanderer's path brings it somewhere interesting. Into a star cluster, through a planetary nebula, into a solar system where a pale blue world harbors billions of living beings, unaware of what's approaching. We don't know when or if such an encounter will happen here. The statistics suggest we're safe for the foreseeable future, but statistics describe probabilities, not certainties. Somewhere in the cosmic roulette wheel, our number might come up, or it might not. We live with this uncertainty, this fundamental vulnerability to forces beyond our control or even our detection. But here's what we do know. Right now, in this moment, we're alive on a beautiful planet orbiting a stable star in a relatively quiet corner of the galaxy. We have the capacity to understand the universe, to contemplate its wonders and terrors, to create meaning and beauty in the face of cosmic indifference. We have each other, our communities, our shared story as a species. The rogue black hole might come tomorrow, or never. Either way, we have today. We have the opportunity to learn, to grow, to love, to create, to explore. We have the privilege of being conscious matter, capable of understanding our own existence and our place in the cosmos. That's extraordinary, regardless of how long it lasts. So yes, a rogue black hole entering our solar system would be catastrophic, possibly civilization ending. potentially leaving no trace that humanity ever existed except for a few spacecraft drifting in the cosmic dark and a faint bubble of radio waves expanding outward at the speed of light. But it also reminds us of something important. The universe doesn't owe us safety. Our existence is a contingent fact, a lucky accident, a brief flowering of complexity in a cosmos that tends toward entropy. Knowing this, what will we do with our moment? How will we use this cosmic eye blink of time that we've been granted? Will we spend it in fear, paralyzed by the knowledge of our vulnerability? Or will we spend it in wonder, appreciating the impossible beauty of being alive, being aware, being able to ask these questions in the first place? The choice is ours, and perhaps that's the final lesson of the rogue black hole scenario. We can't control the cosmos. We can't prevent every possible catastrophe, but we can control how we respond to our cosmic situation, how we treat each other in our world, what we choose to value and pursue in the time we have. Out there in the darkness, the rogues wander on, indifferent to our hopes and fears. But here, on this pale blue, we continue our brief and precious existence, looking up at the stars with wonder and asking the questions that define us as human. What's out there? Where do we come from? Where are we going? Where are you going?